episode of the Supra Build series. So far, we've covered the header and the intercooler. And in this episode, we're going to be covering one of my favorite materials and something I find very interesting, which is titanium. We'll cover a variety of topics, from the different uses of titanium, pie cuts and their proper assembly, anodizing titanium, proper welding techniques, and at the end of the video, we'll put together an intercooler tube for my car. And this video is going to be a little bit more demonstration heavy than the previous videos, so there'll be some good information for everybody to learn. So why don't we dive into it? Roughly 95% of all titanium is refined into titanium dioxide, which is an intensely white pigment used in toothpaste, paints, plastics, and a variety of other applications. In aerospace, titanium is alloyed with aluminum, zirconium, vanadium, nickel, and other elements to make very strong titanium alloys that are used in a variety of applications. Roughly 2/3 of all titanium metal produced is used in aircraft frames and engines, typically 6Al4V. 6Al4V is a titanium alloy with roughly 6% aluminum and 4% vanadium in its alloy structure. And this provides a titanium alloy that is stronger and more desirable to use in aerospace applications. Aerospace titanium is typically used in landing gear, helicopter exhaust ducts, hydraulic systems, and a variety of other applications. And in the example of the SR-71 Blackbird, in the construction of the fuselage. In industrial applications, titanium is used in chemical and petrochemical production due to its extreme resistance to corrosion. In these industrial applications, titanium is used as a vessel to pass corrosive chemicals or media through. Titanium is used in sporting goods such as golf clubs and tennis rackets to make light, strong, durable goods. It's also used in designer jewelry and medical implants due to it being light and biocompatible, or non-toxic and not rejected by the body. Titanium is also used in the construction of firearms and knives due to it being durable and lightweight. It's become common practice nowadays to use Damascus in knife construction. And what Damascus is assorted titanium alloys that are forged into a single billet to create visually striking patterns. In automotive and racing applications, you typically see titanium used in exhausts, induction tubing, and fasteners. Now, this is due to titanium being light and strong, which makes for easy weight savings without a sacrifice in strength. Laid out on the table around me are the various titanium components that I've built for my car. We have wastegate dump tubes, the exhaust, the hot side intercooler tube, and the intake tube. The cold side intercooler tube was unfortunately destroyed. However, I have more materials here to build another one, so we'll do that as a demo later on in the video. Now you may ask yourself, with titanium's high price tag, why use it as opposed to stainless? And the largest reason for this is weight savings. So what I have here are pieces of 39,000th wall CP1 titanium from Ticon Industries and standard 65,000th wall 304 stainless. Now these are both very common alloys and very common materials that you'll see used in exhaust construction. So why don't we weigh them and see what the weight difference is? You can see the difference in wall thickness between the two materials. On the left here, we have the 39,000th wall CP1 titanium. And on the right, we have 65,000th wall 304 stainless. And you can see that both pieces are the same length, which is roughly 4 inches, as well as being the same size, which is 2-inch tubing. Back over to our trusty scale, you can see that it is zeroed out, and that there is nothing on it. And as I press down on it, the weight does in fact go up and down. So with our two materials here, and again, titanium on the left, stainless on the right, let's place stainless on the scale and see what it weighs. The stainless on there, we can see that it has a weight of roughly 6 ounces. Now, removing stainless from the scale, nothing on it, zeroed out, we'll take our titanium piece and place it on the scale. Going back out, we see that it's light enough where it does not even register on the scale. Now, this weighing experiment is small scale, like many of the other ones that we've done as part of this build series. However, when you consider the amount of material used for exhausts, for intercooler tubes, for all the different plumbing components for putting a car like this together, the minute difference in weight becomes substantial. Now, in addition to plumbing components for race cars, titanium is also used in the construction of valves for light, heat-resistant valves, as well as connecting rods to reduce the overall rotating mass of the rotating assembly. Now let's talk about pie cuts. What a pie cut is a miter-cut piece of straight tubing that's used to make a bend. Now you can see with my wastegate dump tube here, this bend is constructed in its entirety of these miter-cut pieces. This technique of bend construction was made popular by old-school Japanese exhaust builders prior to titanium mandrel bends becoming readily available. Building a bend like this is obviously more labor-intensive. However, you maintain a constant wall thickness throughout the entirety of the bend, as opposed to having a thick and a thin side like you will with a mandrel bend. Pie cuts offer a nearly infinite amount of bend radius options, as well as quick direction changes that would be nearly impossible to make with mandrel bends or cut pieces of mandrel bends. Since I have to redo my cold side intercooler tube, I've taken the liberty to order new materials from Taikon. Taikon's been on board with this project from its inception and have treated me exceptionally well with material supply, customer service, and just being good friends. So why don't we open this box up and see how the materials come directly out of the package. For the cold side intercooler tube rebuild. What this order consists of are 4 4-inch pie cut packs and 4 feet of 4-inch straight tube. Now, these materials are ready to weld directly out of the packaging. However, I will be doing some cleanup, some polishing, and alterations to the surface finish to achieve the surface finish that I desire. Each one of these packs comes with 5 segments, which gives you the ability to make a 45-degree bend per 5 pieces. And being that I've ordered 4 of these packs gives me the ability to make 180 degrees of total bend. Now, as I stated before, these are able to be worked with and welded directly out of the packaging. So if I move this a little bit closer to you, which you may or may not be able to see, you can see a clean, workable surface finish both inside and out of it directly out of the package. And these pie cut sections will save you an enormous amount of time spent cutting, prepping, and assembling pie cut pieces, as well as saving you from destroying multiple bandsaw blades in the process. Let's talk a bit about titanium anodizing. Anodizing is the process of applying the beautiful, vibrant colors that titanium is known for. What anodizing is, in simple terms, is creating an oxide layer on the surface of a metal. The most commonly used materials that are able to be anodized in automotive and racing applications are aluminum and titanium. Stainless steel and carbon steel are not able to be anodized because they exfoliate or flake the oxide layer off. Aluminum can be anodized a variety of colors with the use of dye. However, titanium requires no dye to be anodized. The oxide layer that we're putting down on the surface of the metal alters the way that we perceive the light that's reflected off of it. Different wavelengths of light will either cancel or reinforce each other as they reflect off the surface of the material, which the following graphic will show you. If these wavelengths are parallel to each other, they reinforce the color and make it more vibrant. Conversely, if the wavelengths conflict, they cancel each other out and that color is lost. The thickness of the oxide layer that we are applying to the surface of the metal manipulates the cancellation or reinforcement of the wavelengths of light that are being reflected off of it, thus altering the color that we see on the surface of the metal. Titanium can be anodized via 2 different methods. On your left, we have electroanodizing, and on your right, we have thermal anodizing. Thermal anodizing is what people are talking about when you hear them reference burning titanium. What we're effectively doing with this is manipulating the reception of oxygen molecules by the oxide layer. Heating the material energizes these oxygen molecules, allowing them to charge through the oxide layer and contribute to its thickness, thus altering the color that we see on the surface of the material. In front of me is all that's necessary to thermally anodize titanium. What we have is a MAP gas torch, a vise to hold the piece in place, and a piece of titanium. So let me take our test piece of titanium, clamp it in the vise, and do a quick demo on how to thermally anodize titanium. And with our material clamped in the vise, Let's go to a time lapse so you can actually see the color change happen. And after that short period of time, we can see a beautiful, vibrant blue going to purple, going to bronze has appeared on the surface of the material. Since we've covered thermal anodizing, let's now cover electroanodizing of titanium. Rather than using heat, electroanodizing uses an electrolytic solution and electricity to build up an oxide layer. Our titanium piece will be attached to the positive lead on our DC power source, making it the anode. And this piece of stainless steel will be attached to the negative lead of the DC power source, making it the cathode. And this gives hydrogen gas a surface to bubble on. This electrolytic solution can be made easily with distilled water and a phosphate. Typically TSP, trisodium phosphate, which is easily found at most home improvement stores. The one thing to avoid when making your electrolytic solution is using a chloride as opposed to a phosphate. If a chloride is used as opposed to a phosphate, you will create noxious, toxic chlorine gas right in your face, which nobody really wants to do. Now I've made my electrolytic solution, I have my piece of titanium, and my DC power source. So why don't we play around with it and see what kind of colors we can get out of this piece of titanium using this process. Now we have our electroanodizing setup all configured. We're at 0 volts right now on our DC power source. We have our cathode, we have our anode. So let's apply a little bit of voltage. We'll start with, say, 10 volts, 10.5 volts, and see what color that gets us. Simply take this, dip it into our solution, and pull it out. You can see this has gotten us almost a little bit of a bronzish color. So why don't we turn the voltage up another 5 volts. Now at 15 volts, let's see what color that gets us. "15 volts got us a much deeper, darker bronze color. If we increase the voltage even more, 20 volts, see what that gets us. Now we've achieved a beautiful purple color. And in keeping with this theme, another 5 volts. See what that gets. Now we have a beautiful bluish purple. Another 5. We've achieved a vibrant blue. Another 5. A little bit lighter blue color. Another 5. The blue is lightened up even a little bit more. Going to 45 volts. Lightened up even more. To 50 volts. Starting to get a teal hue to it. Let's see what 55 gets us. Starting to get a little bit of a greenish hue to it now. 60 volts. Even more of a greenish hue starts to come out of it now. 65. It's important to mention as you're doing this, never touch the anode and cathode together unless you want to get electrocuted. Now we start to get a yellowish hue to it, which looks kind of wild in person. Let's try 70 volts. Now we get a very vibrant, almost mustard yellow out of it. 75. Yellow became more deep and almost starts to have a green hue to it. Let's see what 80 volts gets. Yellow with a hint of purple to it. Try 85. Almost the same color as 80. It's kind of odd. Let's try 90 volts. Still roughly the same. Let's try bumping at 10 volts and see if that makes a difference. Made a little bit more of a difference. Some pinkish hue started to come out of it now. Let's try another 10 volts. Still roughly the same color, a little bit of pink starting to come into it now. Now if you'll notice, as I submerge this piece, you can watch the voltage drop. And that's due to this power source not having enough amperage to overcome the resistance that this piece is providing. So why don't we max the power source out. Reading 125.3 volts. We'll try to submerge it, again trying to overcome the resistance of this piece and see if we can coax any other colors out of it. Now if you see, as I have it submerged, we were at 125 volts, and now we're down the whole way to 84 volts. Bumping the voltage that last little bit got us kind of an odd pinkish, yellowish, greenish color. Here we can see a side-by-side comparison of the colors that we were able to get out of the two anodizing processes. We can see a nice vibrant bluish purple with the thermal anodized piece, and an odd mustard yellowed pinkish greenish color with the electro anodized piece. Now with thermal anodizing, we are limited in the color palette that we're able to achieve with this process. The purples and blues are about the maximum colors that you'll be able to achieve before you start implementing odd colors to the surface of it that are a bit unsightly. Electroanodizing offers you a wider, more controllable color palette. However, you need a large, powerful power source to overcome the resistance that the titanium piece creates when dipped into the electrolytic solution. For the average enthusiast or hobbyist that wants to begin anodizing titanium, I advise and recommend thermal anodizing as opposed to electroanodizing. This is due to thermal anodizing being cheaper and more effective with larger pieces such as an exhaust, intercooler tube, an intake tube, than electroanodizing will be for those components. And while the color palette is limited, it will allow you to produce these beautiful blues and purples that everybody seeks when working with titanium. Let's discuss the welding process of titanium now. Titanium is welded in DC electronegative or DCEN polarity like many other reactive metals. Examples of these reactive metals would be steel, stainless steel, and nickel alloys. Gas coverage for any reactive metal is extraordinarily important to make a proper, structurally sound weld. These reactive metals will pull in atmospheric contaminants during elevated temperatures during the welding process. And the impregnation of these atmospheric contaminants can compromise the structural integrity of the piece that you're welding. I have in front of me 3 different welding gas nozzles that you'll typically see used in titanium welding. From right to left, we have a standard number 8 gas lens, we have an SPW number 14 gas lens, and we have a Dogfab SSBBW gas lens. If I hold these up to the camera, you can see the drastic difference in the outlet size of each one of these gas nozzles. Practically speaking, what this means is that the larger the outlet size of the gas lens that you're using, the larger the area of gas coverage that you'll be working with during the welding process. When working with larger gas nozzles, such as the SPW or the Dogfab nozzle I have sitting in front of me, you will increase the amount of argon that's flowing out of it to increase the velocity and to protect the weld that you're producing from atmospheric contamination. Now this will result in a larger amount of argon being used, which is an unavoidable consequence of this type of welding. However, the benefits of this additional gas use far outweigh the consequence of having to spend more money on gas. To the right here, we have a pair of TIG Aesthetics back purging plugs, as back purging is a quintessential part of the titanium welding process. Exactly as we shield the outside of a piece of reactive metal that we're welding, it's important to shield the inside of it from atmospheric contamination as well. And what back purging is filling the volume of the piece that we're welding with inert gas, typically argon, to prevent this oxidation from happening. Failure to back purge titanium will result in a white, chalky substance being deposited on the inside of where you're welding, as well as a lack or inability to achieve full penetration. Setting up the back purge is very easy. Now have there 2 pieces of titanium that we anodized earlier, as well as a center linking piece to provide me with 2 welds to do for this demonstration. And what we're going to do is take these 2 plugs and put them in either end of the tube. Now this plug is just a simple vent to allow oxygen to be pushed out of the inside of the tube. And this plug is what we're actually attaching to an argon bottle to push argon into it and to disperse the oxygen from the inside of the tube. So all that we're doing is taking our piece, inserting a plug into one side, inserting a plug into the other side, and then taking a gas line, attaching it, and allowing gas to be pushed through it. I'm using a secondary bottle of argon to purge with for this demonstration. You can see I have my flow meter attached to the bottle. It's open and gas is flowing out of it. If we come down here to the titanium piece, and if I'm quiet, you can hear gas exiting the tube. And what I'll do now is produce a couple of welds on this tube to show the different gas coverages that these cups can offer, as well as what happens when you back purge and when you don't when welding titanium. Here we have our first test weld, which I used all 3 different cups on to show how well they work. I started out with the number 8 cup, and that's where you see the blues and the colors on the outside of the tube. And why you see that is the cup was not large enough and not able to provide adequate shielding for titanium to prevent it from pulling in atmospheric contamination. As we keep rotating around, where it starts to clear up is where I was using the number 14 lens. And you can see the complete lack of color throughout the entire section of the tube. And towards the end, where you see absolutely no color in the weld, is where I was using the large dog fab lens for it. And now I have my back purge set up and pushing oxygen out of the tube. You can see up here at the flow meter, it is flowing gas out of it. So let's do another weld and see how back purging affects it. Here we have our second test weld. Again, starting out with the number 8 cup, you can see all the colors throughout it, again not able to maintain an adequate amount of shielding. Going a little bit farther, where the colors dissipate, is where we moved on to the number 14 cup. The 14 cup provides an adequate amount of shielding, however it limits the amount of distance you're able to travel with the torch before the weld becomes exposed to the atmosphere and ripe for contamination. Going even farther, where we see no colors in the weld towards the end of it, is where I was using the large dog fab cup. This cup provides an unparalleled amount of shielding coverage, however, you use much more gas with it. Now, I want to do one more test with this piece of tube before I cut it apart and show you guys the inside of it. Now what I'm going to do is to take each one of these cups and to do a long continuous weld. And what I'm aiming to do with this is to see how well they maintain shielding gas coverage over a 6 to 8 inch span. Now I will have the back purge hooked up to it just to make the welding dynamics a little bit easier on my end, but this will give us a very good idea of what cup is proper to use for a reactive metal like this. And here are the results. Starting off with the number 8 cup, we see almost nothing but colors the entire way through, right up until the very end where it was allowing post-flow to happen. Now we can clearly see that this cup was not adequate whatsoever for welding titanium, as all these colors are just atmospheric contamination that's now impregnated into the weld. Rotating it over, we have the number 14 cup next. And with this weld from the number 14 cup, we see a substantially less amount of color involved with it, meaning that there is less atmospheric contamination that was pulled into the weld. However, this cup is not designed for long runs like this on reactive metals like titanium, so we still do see a fair amount of color in the weld. And finally, we make it over to the dog fab cup. Now we see a little bit of color through it, but overall it's fairly gold or straw colored, meaning that there is almost no contamination pulled into the weld from the atmosphere. Now this cup is more adequate for long runs on a reactive metal like this. However, the best option still is a trailing shield as opposed to running a normal gas lens or gas nozzle setup. Now I have the piece cut in half with our back purged portion on the right and our not back purged portion on the left. So let's take a look at the inside of it and see what they look like. Now the non-back purged portion may be slightly difficult to see with the light. We can see all the nasty, white, scaly mess on the inside of it, signifying no gas coverage and a ton of oxidation. Now this non-back purged weld would not be a structurally sound weld and not be one that should be put into service if any bit of longevity is expected out of it. It's difficult to see in the video, but the weld is very convex to the surface of the material because it is not able to penetrate through to the inside of the tube. Conversely, our back purge tube, you can see the inside has no scaly oxidation whatsoever, and a crystal clear, almost copy and paste of the outside weld on the inside of the tube. Now this is a full penetration weld the entire way around the tube. And this is one that is structurally sound and one that would have no issue going into service and providing longevity to the end user. Now this should give you an idea of what you're looking for when you're examining titanium parts. If you see a nice crystal clear shiny weld on the inside of the tube, meaning that it has been back purged and welded properly, you have no problem using that piece. However, if you see the white chalky scaliness on the inside of the tube, signifying that no back purging and an improper welding process has been used in the construction of that part, run. The next topic we'll cover is assembling pie cut pieces. You can see I have all the pieces for my new intercooler tube laid out in front of me. And I'll show you how I do this, how I align them and how I get them to fit together properly. Each one of these pie cut pieces is cut out of a seam welded piece of titanium tubing. So they do have a seam weld on them, as you can see right above my thumb here. So what I like to do is to align these seams on the pie cut bend that I'm making. And what these seams do is serve as a reference point so you can make a true aligned bend, as opposed to having the pieces be skewed one way or another. And I'll fit these pieces by hand as I go around and tack them to each other as I'm building a bend, to make sure there's no overlaps or misalignment of any of the pieces that would become unsightly during the welding process. This piece that you saw me just tack together actually serves as the first bend for my new intercooler tube. All the other pieces here become the different bends that are involved with putting this tube together. So now let's assemble those bends. And there we have it. Your cold side intercooler tube all refabbed, fitting nicely. All the pie cut sections fit together well. There's no substantial overlaps on any one of the joints. I'm pretty satisfied with it. Now, the next thing to do is to anodize it. Now I have the piece all clamped in the vise and ready to be anodized. When I'm anodizing larger pieces like this, I choose to use this large flare torch as opposed to a standard small MAP gas torch. And this is due to the large amount of area that I'm going to be anodizing, and it being almost impossible with a small torch to apply an adequate amount of heat to get the piece to change color. And now, after the anodization process, you can see nice blues and purples all throughout the tube. I'm going with a blue theme on the car, so this will match up pretty much perfectly with that. It took a little bit longer than I expected it to anodize this, but you have to be careful with the amount of heat input that you put in, as when you start to get into these blues and light blues, the color can run away from you very, very quickly. But overall, I'm very satisfied with the colors I was able to achieve on this. Now I did just finish anodizing this piece, so it is still scalding hot. So we'll let it cool down for a few minutes and then put it back on the car to see how it looks on there. Here we have the tube up in the car now. You can see that color really, really pops. It looks exactly the way that I wanted it to. This will match very well with all the other blue titanium fasteners I'll be using throughout the engine bay and the rest of the build. I'm very, very happy with that. The last demonstration we'll do for this video is welding the hot side intercooler tube. This will give you guys an idea of what titanium looks like post-welding after anodizing it prior to welding it. And this creates an aesthetic that may not work for everybody, but I like it very much for my parts. Here's the finished product, the hot side intercooler tube. You can see little to no color throughout all of the welds. And you can also see that the welded portions the anodizing has been burnt off of it. And I prefer this look over burning after you weld it. I think it looks a little bit classier, a little bit more refined, and you can really see the detail in all of the welds rather than covering them up with a bunch of colors. And looking at the inside, we can also see nice full penetration welds throughout it. This is a very strong piece. It will serve me well for years to come. Now initially I was planning on welding all of my titanium parts up as part of this video. However, that would take a substantial amount of time, and I have other work that needs to be attended to rather than spend time on my own vehicle. Now we're just about finished with this episode, but there are a few considerations and points I'd like you to take away from this. Now the first point I'd like to make is that titanium is a light, strong material that is very versatile in motorsports fabrication. You can use it in crafting your exhausts, your induction tubing, and a variety of other applications. The second point is that pie cuts do take more time to assemble and weld, but they do also provide you with uniform wall thickness throughout bends, as well as old school aesthetics that do complement many builds. The third point is that anodizing creates beautiful, vibrant colors on the surface of titanium by manipulating the thickness of an oxide layer that's placed on the surface that affects the way that light is reflected off and affects the color that we see on the surface of the material. The fourth point is that titanium's welding process is much more involved than any other reactive metal due to its extreme reactivity or desire to pull contaminants in from the atmosphere. This propensity for contamination can be mitigated by properly shielding it with inert gas, typically argon. One other point I did not touch on earlier as far as the welding process with titanium is concerned is the stickiness of the filler rod to the surface of the material. Unless you add filler rod in a very precise location, which is typically the hottest, most liquid part of the puddle, the filler rod will stick to the surface of the material like glue. Now from time to time this will result in you having to terminate your weld and to fight the filler rod off of the surface of the material. As you get more experience with welding titanium, you can mitigate this stickiness to some degree by figuring out a consistent way to add filler rod to the hottest part of the puddle. And the fifth and final point that I'll make is that back purging is an essential part of a proper titanium welding process. Failure to back purge will result in welds that are not structurally sound and welds that can fail. And these weld failures can result in costly repairs or, worst case, replacement of the parts if they cannot be repaired. Like my other videos, I have a few people that I'd like to thank for making these titanium parts possible. Firstly, we have the whole crew at Tycon Industries for supplying me with the tubing, the pie cuts, the flanges, and virtually all the materials that have gone into all the titanium parts on my car. Secondly, we have Market Proper Fabrications for getting me the beautiful titanium velocity stack that sticks through my bumper. Third, we have Mike Furyk from DogFab for getting me the awesome SSBBW TIG cup that allowed me to create these colorless welds on the titanium parts that I'm building. And last but not least, we have Brad at TIG Aesthetics for getting me the silicone back purge plugs that have made the back purging process incredibly easy for these parts. All these guys are linked in the description below, so if you need any titanium parts or tools for your vehicle and your project, be sure to contact them and they'll get you set up. Well, that wraps it up for this episode. As always, be sure to like, comment, and subscribe, and we'll see you next time.